Hey, and welcome back. In this section of the course, we're going to cover the modeling of soil fluxes with a particular emphasis on soil moisture, though a very analogous set of equations apply to the modeling of soil temperature. So, as a reminder of where we were, in the last set of videos, we introduced Fick's law of diffusion and went through how we can take a diffusion, a flux equation like Fick's law, and discretize this in space by substituting a dc dx with a delta c delta x, and discretize this in time by replacing our flux, which is a dc dt, with a delta c delta t. And we could do this dual discretization such that we could actually model some discrete amount of, in that case, pollutant moving from one place to another in a discrete amount of time. And we end up with a simple set of conservation equations that say concentration at one point in time, the concentration at the next point in time is a concentration right now, plus or minus some amount that's moving in or out. And that amount that's moving in and out is, again, this flux, this minus d delta c delta x times a delta t. It's actually something we'll get to numerically implementing later, but I would argue it's actually a simpler model than the logistic model because there's only one equation, d, and the only thing that's really going on is conservation of mass. Where it is, when you move something out of one grid cell and put in the other, you add it to one and subtract it from the other. We saw how instead of having an analytical solution for doing this on an infinite tube, we could discretize this on a finite tube by dividing it up into grid cells, giving them a discrete delta x. And that in practice, you would do this numerically just by setting up loops. So you loop over time like we do in population models, and then within time, you're going to loop over space and move mass from one cell to another. We showed how this numerical simulation actually behaved compared to the analytical solution. And we ended by talking about how these flux equations are ubiquitous. And we talked about, in this one, we introduced Fick's law, but that Ohm's law for electricity, Fourier's law for thermodynamics, Darcy's law for fluid flow are all examples of flux equations. You can use flux equations even beyond that. Like if you want to model the spread of an invasive species across a landscape, you could do it. You could do dispersal of plants or animals or microbes using a diffusion flux equation, or that these sorts of flux equations end up quite a bit. We end up using quite a bit, and many of them are relevant to the environmental sciences. So we're going to use Fick's law to model pollutants. We're going to use Darcy's law to model hydrology, Fourier's law anytime we care about the energy budget of a system. And that very similar laws with a little bit more complexity are what govern fluid flow in the oceans and the atmosphere. So the Navier-Stokes equations are very similar to these flux equations, but a little bit more complicated. But I think understanding these approaches would set one up very well to understanding those as well. So the goal here in this unit, which is going to focus on soil fluxes, is to first give an example of an important real-world application of flux models. In this case, we're going to use it to model soil moisture, basic hydrological process. And more importantly, we're going to use this to illustrate how, like with the population models, we started with a very simple exponential growth model, and we built on that incrementally. So here we're going to start with a very simple Darcy's law, which is just a basic flux equation. We're going to build on that incrementally by making the parameters in Darcy's law functions of other things. We're going to use this as a way of illustrating these numerical approaches and how these numerical approaches allow us to relax a lot of the assumptions of that simple 1D diffusion. So, we now can control the boundary conditions. We can control that assumption of homogeneity. So we can make the soil, have different characteristics in different places, spatially. We can make that non-reactive assumption. We can make mass enter or leave in other places. We don't have to start with a fixed mass. We can continually have precipitation events add water in, and evaporation and transpiration remove it. So we can relax kind of all of the assumptions, but we're going to stick. We're going to relax all the assumptions, but at the same time, for illustrative purposes, we're going to stick with just a simple 1D model, which is actually, a really important application of these soil moisture models, and leave the generalization to, 2 or 3 dimensions, just to the general understanding that if you can understand the 1D version, really extending that to 2 or 3D just means more loops. Really nothing other than that. Okay, so let's dive into thinking about soil moisture a little bit. So it's a key part of the hydrological cycle, and we have this balance between precipitation coming down into systems, into terrestrial systems, evaporation and transpiration, being the vertical fluxes back out to the atmosphere, this downward percolation flux into storage and subsurface flow, this runoff over the surface, and then ultimately those are leading us to stream flow, which is going to then move us from our terrestrial systems to our aquatic systems. And through all of this, this soil moisture plays a key role in basically all plant life. So, all plants need moisture, and they need all terrestrial plants are growing in the soil, and that's going to be native ecosystems, forestry, agriculture. The ability to understand and predict soil moisture is absolutely critical to agriculture. It's critical to all the animals that depend on these ecosystems, people, all of our biogeochemical cycles beyond just the hydrological cycle, but the nitrogen cycle, carbon cycle, silica, sulfur, like all of our biogeochemical cycles are tightly coupled to, so what goes on in the soil and the moisture status of that soil. And then also this coupling, not just to the water budget, but also the energy budget, because that evaporative fluxes are a major part of the energy budget of the system. And also mentioned that the actual, if you wanted to model the energy cycle, you would follow very, very similar sets of equations. A little bit more detail about how we think about soil moisture. It's something that we can measure in a wide different ways. So, data would be important for any actual model calibration or validation or application. So here's it on the right is an example of this is a view downward vertically into a pit where these soil moisture sensors have been installed horizontally into the soil, measuring soil moisture at a whole range of depths from very shallow down to fairly deep. I believe this pit actually is 4 meters deep, up through a range of near surface technologies, portable technologies, and including airborne and satellite technology. So this is NASA's SMAP satellite, the soil moisture active passive, that actually can measure the top 2 to 5 centimeters of soil moisture status based on microwaves. So it's kind of crazy. So we actually can map soil moisture coarsely. This is I think a 9-kilometer resolution for that product, but you can still map soil moisture across the globe. So when I think about soil moisture, I usually envision, well, first of all, I would say we're focused usually on in this particular case, on the near surface. So I'm not going to deal with kind of deeper hydrological processes. I'm going to deal with the kind of the near surface, which is, usually where a lot of the action is in terms of evaporation, transpiration, and biogeochemistry and ecosystem water use. So imagine that you're thinking about this profile of soil. So I often think of it as like a cube of soil, say, and to make a lot of these units easier, I usually think of it as a 1 by 1 by 1 meter cube of soil. So if this 1 meter cube of soil, say it's at the surface, maybe there's another one stacked underneath it going down vertically. And in any of those kind of cubes of soil, you've got a mix of things going on. So you have a mix of solids, gases, and liquids. So the solid part of soil is the obvious part, because we think of soil as a solid thing. But in practice, various soils are usually only a little bit over half composed of solid material. Our clays, our sand, our silts, and rocks. But there's a lot of pore space in your average soil. And that's pore space, which, in this particular example, where, this might be envisioning, 1 meter worth of soil, 45% of that is either gas or liquid. And it's, if we're on the surface, it's going to either, wet up and fill and saturate in big rain events, or drain out and dry out during dry periods. And so that soil moisture is going to be constantly fluctuating between wet conditions and dry conditions, depending on the system. And so when we want to think about measuring the soil, we need to keep track of how much moisture is in the soil relative to these capacities. So an important reference point for any particular soil is its saturation point. So, how much pore space actually is there. So, how much water can you put into that, cube of soil before it just fundamentally fills up. So that's what we call the saturation. The next point here is called field capacity. And that would be, if you imagine you took that block of soil and it wasn't sitting in the ground, but, you just picked it up and you let the water drain out of it. Like if you had a sponge in the sink and you picked it up and there's going to be an immediate amount of water that drains out. So, there's, I think a sponge is another good analogy. So when the sponge is in the underwater, there's a certain amount of water in the sponge, but if you picked it up, you'd lose some. And so that would be that amount you would lose would be that difference between saturation and field capacity. Field capacity is kind of after you've accounted for gravitational drainage. That's why it's labeled gravitational water. Then you have this additional bit of what it's labeling here as available water, which is the water that plants can potentially extract. Then there's going to be this wilting point, which is the point where most plants will shut down their ability to extract water from the soil. And so the soil can continue to dry out through evaporation after that, but it's transpiration, you're going to get much less uptake by plants. And then there's this other point that wasn't in this figure, but often reference the dry soil capacity, and that's under normal atmospheric conditions and temperatures, not baking a soil in an oven, the soil's not going to ever completely dry out because there's going to always be kind of water held deep in the pores. So there's this kind of dry soil capacity. So yeah, there's these various reference points, and any particular soil could be anywhere between that dry soil capacity and that saturation point. Cool. So kind of armed with this understanding, this conceptual perspective on how to think about the soil and its mix of water and solids and air when it's not filled with water. I'm going to wrap this video up and move on to thinking in the next section about how we actually model the movement of water through the soil. Thanks.